In this lecture, we will be studying the concept of nonlinear regression. So a nonlinear regression can be written in this general fashion here, where, as in the linear case, y sub I is the ith observation of the response variable, x sub I is a vector, it's the ith observation of our vector of predictors, and so we can think of it as this vector with p entries, x1 through xp, which are our predictor variables, and then beta is the unknown parameter vector. And so this is just a more general way of writing the idea of a regression, and we also note that we need to add our epsilon I. So as usual, epsilon I is our white noise 0 sigma epsilon squared term. We look at this and recognize that if f is a linear function of the entries of xi, then this is simply a linear regression, or a multilinear regression. This is just a more general way of writing it, where f can just be any function. We can still use the least squares approach for our choice of beta. And so we want to minimize over beta the sum of I ranging from 1 to n of, as usual, our observation, yi, minus the fitted value at the predictor xi, given the beta parameter vector, and we square that. And so we recognize that what we have here are the errors, right? This is the difference between the ith observed response value and the ith fitted or predicted value for the response. So once we have this results in what we typically call beta hat. So that's going to be our best estimates for this beta vector of parameters, and that gives us our predicted values. By plugging in that beta hat to the function, we get yi hat is f of xi, and notice here we have a beta hat. So we get our predicted values when we plug in beta hat, and then we get our residuals, our epsilon I hat, as the difference between the observed ith value and the ith fitted value. This can be a bit more complicated than the linear case because things depend heavily on f. With the linear approach, we know that this is a convex function, but given that f could be anything, it's possible to lose convexity here. So you may not have as nice of a problem for a least squares problem as you get with the linear case. Well, actually, generally you won't. It works out very nicely in the linear case, but things can be very heavily dependent upon f here. Let's do an example and see how this actually works. And a natural example is one in the context of bonds. Let's consider the example of a zero coupon bond. And so suppose we have a zero coupon bond with par price $1,000 and maturity capital T. What this means is on a timeline, if we're standing here at, say, time 0, at later time, capital T, this bond will pay $1,000. And so that's what it means with by par price. So it's a bond that has exactly one cash flow in the future. if we are considering an interest rate of R with continuous compounding, then we can figure out the price of this bond here at time 0. And we do that by discounting that $1,000 back t units of time. And we know that that price, say P, is that $1,000, and to discount it back, we multiply by e to the negative RT. And there are ways you can derive this. This comes from our continuous compounding interest rate problem. And the idea is that this is the amount of money that you would invest in the money market account at interest rate R that would grow to $1,000 at time t. So this would be the arbitrage-free price of this bond at time 0, e to the minus RT. Now, let's make the problem more interesting and assume that we have many such zero coupon bonds. So we have a zero coupon bond for each of these different maturities, T1, T2, up to Tn. And we assume that they all have the same continuously compounded interest rate R. And it's important that it's the same. There's no R sub I here. We're assuming they all have the same rate. And it's important to note, this is not a realistic assumption. In terms of just the reality of bonds is you'll have different rates for these different bonds. But one classical assumption in mathematical finance is the existence of a risk-free rate. So you may be using these different bonds to come up with an estimate of what you should use for that risk-free rate in some other problem that you're working on. According to our model, the price of the ith bond at time 0 would be, let's call it P sub I, 1,000 e to the negative R times Ti. In theory, this should be the exact price of the bond. This is the arbitrage-free price of the bond. But in reality, these bonds are trading. So the real price, the actual price of this bond likely differs. Recognizing that this is the theoretical value that the bond should take, let's call this Pi hat. That should be our fitted value. And suppose further that we have data from the market. You can actually look and see what are these bonds trading at. So we have prices, and again, market prices, P1 up to Pn. And we can think of this as a nice regression model. We can say that our model is that Pi is 1,000 e to the minus R Ti plus epsilon I. And what we have is this being our nonlinear function. So we have f of Ti and R. We thus now proceed with our least squares problem to estimate our parameter R. So we want to minimize over all the possible values for R. We sum over all the bonds, sum I going from 1 to n, and we have our observed market price minus our function f of Ti R squared. And of course, we know that this becomes the minimization problem over all the possible interest rates of P sub I minus, and we know our function f, we have 1,000 e to the minus r times ti. And we square these. And so this is our least squares problem. And this is a nice problem. This is actually going to be a convex problem. And it's a function of only one parameter. And so we can take the derivative, set it to 0. That's our first order condition. And then we can check with a second derivative that as long as we have a function that's going to be concave up in R, we'll get a minimizer. And so this will give us the continuously compounded interest rate that syncs up with that given bond data. And one may say, well, this doesn't feel realistic. But it actually is quite realistic because in real life, we have zero coupon bonds of different maturities called strips. And really those are just constructed bonds. They're constructed to be zero coupon bonds. So these things actually do trade. And this is a way that you can estimate that continuously compounded constant rate of interest that you might be using in some other sense in financial modeling, such as in option pricing when you need an interest rate for the Black-Scholes model. But this is just one example of one possible nonlinear regression. And really the point of this is to know that linear regression is just a special case of using a linear function for your regression predictive modeling. You can use anything. There's no preconceived notion that things have to be linear. But of course, linear regression is a very nice case and by far the most commonly used and implemented case. But it's important to see that we have a much more versatile machine here with regression when we can think of using nonlinear functions for our fitting of predicted values.